about XRD. What's that? Oh, looking at the date? Yeah. So we're going to talk about XRD methods here for a little bit, and I don't know if it'll take up the entire class time that we have. We can talk about it more. I've used XRD, which stands for X-ray diffraction, or X-ray diffractometry. We just call it XRD for short because it's easier. But it's a very useful analytical technique which utilizes X-rays to determine the mineralogical composition of fine-grained material. Okay. And unfortunately, we don't have one here, which is something that I'm working on trying to remedy here in the future, hopefully. So we can have one so we can do fun stuff with it. But for now, it is important that you guys know how to use one, or at least know how to prepare the samples to then use the machines, because most larger universities and even a lot of colleges have them. So depending on your career trajectories, if you're planning on continuing education, or you may end up going somewhere and working, for a university, maybe as a researcher or something, this would be a really useful tool, really for any aspect of geology that you guys might go into, because really it's a very valuable tool because it can be applied to all the different fields of geology. You can use it for, say, looking at the different types of polymorphism in samples that have, clay-fired pots, for example. You can look at to see if a particular technique maybe alters the clay minerals in there as a result of heating them up or grinding them even for the perforate, which is one of the things you have to do to prepare the samples for XRD. So. Okay. No inputs detected. Okay. So, X-ray diffraction and X-ray crystallography. Okay. So let's start talking about what diffraction is first. And diffraction is the various phenomena that are associated with wave propagation. Okay. So, for example, bending and interference of waves. Okay. And when the wave passes by an object, that disrupts the wave. Okay. So here we have an example down here of a CD where you turn it upside down and you shine light on it, and the light ends up being diffracted into all the different colors. Okay. We could also look at it from the standpoint of sound, okay, or waves or light in the form of waves as well. Okay. So as a result, you have a light source, and what's happening here is you've got a tennis ball, but the light is actually diffracted around your golf ball there. So, what does diffraction have to do with this? Well, diffraction patterns are unique to each individual mineral. Okay. And they're very complex, but because like I said, they're unique for each mineral, they give off a particular signature which is recognizable. So the complex patterns of a diffracted wave result from the interference between different rays that travel to the observer along different paths. Okay. which is what we can see going on here. It's just this. There you go. Okay. So diffraction effects are most noticeable when your wavelength of the waves is similar to the size of the diffracting objects or the apertures. Okay. And this is just a note. This is not something I need you guys to memorize, but it's important to understand how the XRD process actually happens rather than just you put something into the black box and you get out information. It's important to understand how the black box works. So, diffraction of visible light is diffracted by slits or objects that are spaced at approximately 500 nanometers or 0.5 micrometers apart. Okay. So we've got our visible light spectrum, right? Infrared, UV, 3 different bands of UV. Okay. What?
Okay, I got it right.
Okay. So, when we talk about X-rays and crystals, the wavelength of X-rays are about 10 to 0.01 nanometers, which is approximately 1,000 times shorter than the wavelength of visible light. Okay? So we look on here, we see X-rays, they fall in between here and here, and our visible light spectrum is just right in this range right here. Okay. So X-rays should be diffracted by slits or objects about 0.1 nanometer or 1 angstrom. So we're talking really thin. So, the spacing of the atoms in the crystal lattice are on the order of 0.1 nanometers. Okay. So X-rays have wavelengths on the order of 0.1 nanometers, and X-rays are then diffracted by the crystals to create a specific pattern. So the way that an XRD works is you have an X-ray tube, which is your source of your X-rays, and usually you can actually adjust the voltage on these. Usually they're between, the adjustments are between 10,000 and 40,000 volts. I've seen up to 60,000 though. Then your X-rays pass through a lead screen, okay, which basically filters out a lot of the X-rays, so you can actually then what's the word I'm looking for? Direct. There we go. Direct the X-rays. Then you have your sample, okay, through which the X-rays are bombarding your sample, okay, and they are then diffracted buy your sample because they interact with the crystalline structure, all right? And then as a result, the light or the X-rays or light passes through it, and you get a spot from the beam, you get spots from diffracted X-rays on a photographic plate. Okay. So that's basically what the machine does, and I'll show you a couple pictures of different machines as well. But where did this idea come from? Well, it started back in 1919 when A.W. Hull noted that every crystalline substance can produce an X-ray diffraction pattern. Okay? And the same substance always gives the same pattern, and a mixture of substances each produces its pattern independent of one another, although you can have some patterns that have peaks that overlap one another, and then things get a little trickier. But the diffraction pattern of a pure substance is basically like the fingerprint of the substance, and from that you can determine exactly what the composition is. So minerals can be identified by the diffraction patterns. Okay. So, well, what does that actually look like in the machine? What does the machine actually look like? What is it actually doing? Well, usually inside the machine, okay, for X-ray diffraction, you have your wavelength, you have your 2 theta angle, okay, which is the angle at which your incoming rays are hitting your sample in reference to, let me start over. The incoming rays are coming in and impacting your sample or colliding with and being diffracted out of your sample at a particular angle. That angle, your 2 theta angle, is determined based upon what the incoming angle is versus the outgoing angle. Okay. So in papers you hear them refer to the 2 theta angle, and this angle can change. Okay, as you can see here, your 2 theta angle is different than it is here. All right. And sometimes you hear you'll see or hear someone referred to as D-spacing. Okay. And that refers to the space in between each individual atom that makes up the crystalline structure. Okay. So depending on your mineral, your D-spacing will be different. Okay. So what we can see here is the your crystal here, and these are the atoms inside your crystal, these blue dots, all right, and this is your D-spacing. So you have your incident plane wave, which comes in, all right, and you have constructive interference when n, okay, your wavelength, okay, so some number for your wavelength is equal to 2d sine of theta. Okay? And we can figure that out. And in most cases, the machine tells you all this. And it does this calculation for you. Hopefully this one works. Because I didn't double check. Ah, it does. Yay. Oh, you guys can't see it. Hey, again. Okay. No, I can't see it. That doesn't work. Hang on. So, you see, here you have your incident wave, here you have your reflected wave, these blue dots are your sample. Alright, in this case we have it set, so our wavelength is 0.6 nanometers. Alright, our angle is about 45 degrees, which is about normal for it. And your plane spacing or your D spacing is 0.3 nanometers. Okay. So we can change this. So if we want to increase our D spacing, right, or we want to adjust the angle, and we can change your wavelength. Okay. So these are all inputs that you can actually change. You can't really change the D spacing because, well, the D spacing is determined by your mineral, so I guess it does change, but you don't necessarily have control of that. You can change the angle, your theta angle, and you can change your wavelength as well. Those are inputs that you can control. So yeah. Yeah.
What is N?
N is just an integer for determining your wavelength, but N is influenced by your angle, and it's influenced by your wavelength.
Mm-hmm.
So N is just some number.
Okay.
And you can solve for what N is if you know everything else. Alright. So, in this case, we have multiple D spacings, and this could be interpreted as, okay, we have multiple different minerals in there, or the orientation of the minerals is different, and that's actually true in a lot of cases with samples that you have, because when you actually take your sample and get ready for it to be analyzed, you have to grind it up into a fine powder. Now, if you're dealing with clays, this can be sort of problematic because clays like to lay flat, and if you put them in a flat tray, you're going to get some interference because all the X-rays are hitting those clay minerals at the same angle and interacting with your atoms inside the crystalline structure in the same manner, and that doesn't give you a very good picture as to what the XRD pattern for that mineral is. Because in order to get basically good intensities for all your peaks, you want to have the minerals that you ground up, or the minerals that you ground up in your sample tray to basically be in all different orientations, so that the X-rays, when they do pass through it, they give you a complete picture of what mineral you're dealing with, or minerals as it may be. So the inside of an X-ray diffractometer looks sort of like this. And what you have in there, this is right where you would put your sample, and usually it's a small tray that you put in there. And the one that would be used for this particular machine here, I'm not sure, it looks similar to the one that I used in grad school, but there's many different manufacturers have many different types of XRDs depending upon what you're planning on using it for. There's different types of models. There's tabletop. There's ones like this, which are they usually stand about this tall, and they have an X-ray tube in there and everything. Which is another important thing when you use an XRD. You're dealing with X-rays, so you want to be careful. Make sure that the machine is closed while it's running, while the X-ray tube is hot. And most modern XRD machines, they have fail-safes built into them so that you can't necessarily open it while the X-rays are occurring, but there are some older ones and some different models that don't have all of the really nice safety features. But anyways, so your sample tray looks pretty much like a normal slide, petrographic slide, but the thing with this is that usually it has like a little indentation in it where you can actually put your sample in here. Okay, and it's not very deep, the indentation in there, and I mean, depending upon, you can get different slides that have different depths depending on what minerals you're using. Like if you're using clays, you might want a little bit thicker one. It's important, depending upon the type of sample holder that you use, that you don't necessarily pack down the sample, because then you'll get, like I said before, you'll get the orientation of the minerals basically all oriented in the same fashion, and you don't want that. Some other sample trays are kind of circular, and you put your powder sample in here. Okay. And some XRDs, the nice ones, have multiple sample trays in there, so you can just throw in like 6 samples or 12 samples and then come back when it's all done. Because usually your typical scan, depending upon the scan speed, which can, you can also input the scan speed, so how many degrees the machine scans per minute. So usually, going back for a second here, when we talk about this 2 theta angle, you typically, or 2 theta angle, you typically adjust it between 0 and 90 degrees. Okay, and the machine will then take your, go forward, come on. It will take your X-ray tube, which is this guy over here. I think. No, this is your X-ray tube over here. Your X-ray tube, and it will basically turn these two. Your detector and your X-ray tube will basically rotate to change the angle. Okay. So that you can go through and it will detect from 0 degrees. Usually don't set it at 0. Usually it's like 5, maybe 5 to 90 or something like that. And, or 5 to 75. And you can also adjust the scan speed, which is like I was saying, you can usually, usually I used to set mine to, like, if I wanted a really good scan, like 0.5 degree per minute. So depending on how many degrees you want to be covered by your scan, usually scans and how slow you set it. Usually most scans that give you good resolution only take about 45 minutes to maybe an hour and 25 minutes. Yeah.
What would be the benefit of putting it 90 degrees? I don't really see anything.
Well, it depends. The angle angles that you cover will how do I say this? There are certain minerals that are picked up by the XRD based upon what angles it scans. Okay. So if you're looking for a certain set of minerals that you think are in your sample, or if you know that there are some minerals in your sample and you just want to confirm it, then you can punch in the different angles for the minerals and have it scan for just those specific angles.
Okay. And so, are there any minerals do you know that can be affected by X-rays? Do you know that higher, like UV can interfere with?
Not that I know of.
Just not okay.
Not that I know of. Or at least that I've encountered. But there are some minerals, such as, well, calcites and aragonites and different carbon minerals, which can be altered by the preparation process of just grinding the minerals up. So you can have alteration of your minerals to different polymorphs before you even get them in the scanners, which is sometimes a problem. Because especially when you're dealing with multiple polymorphs of the same mineral and there's not a lot of documentation upon what causes those polymorphs to form, and you detect it in your scan, you're like, okay, well, what caused this? And why is this here? Sometimes you don't have a good answer for it. Maybe contamination of the sample. It could have been contamination of, it could have, also when you, I'll get to that in a second. So anyways, cut myself off before I started rambling. Anyways, so what you were looking at in the previous slide here was pretty much this. Okay, so we see here, all right, this is this. So in this case, we can see here's our X-ray tube. They sort of flipped it around on us, but here's the diffractometer circle. All right, your X-rays come out of the X-ray tube, go through the divergent slits. Your powdered sample is usually here. This is your axis. You can rotate those two around. Here's your counter. Okay. And your X-rays that are reflected back off of your powdered sample, and you have your receiving slits in there as well. Okay. It's actually not too difficult of a machine, although I couldn't build one, but they, depending on what model you get, they can be kind of expensive, and what bells and whistles you get with them.
Just buy a lot of Scotch tape and photo paper. Try to find that one.
So, XRD patterns, quartz, and this is referring to the D-spacing, and here's your 2 theta angles. Okay. So when we talk about our D-spacing, all right, and our 2 theta angles, all right, our 2 theta angles are basically what we get, okay, for our peaks, for the different patterns of each mineral. And in most cases, most samples that you run through, they're going to have quartz in there. So if you know or are pretty sure that your sample has quartz in there, it's a good idea to filter it out, because what ends up happening is basically filter out the signal for your quartz, because what ends up happening is quartz can mask the signatures of the other minerals that you're looking for in your sample. So then you get basically a depressed peak for all your other samples, because your quartz pattern is so high, okay, and so dominant in the sample that it basically is noise for everything else that you're looking for. So if you're not looking for quartz, chances are you might want to filter it out so that you can get a good reading on your other samples. Yeah.
Well, what's the vertical axis?
The vertical axis is CPS, which is counts per second, which is an arbitrary, not necessarily arbitrary, but it basically is the intensity of your peak, and basically represents the percentage to which your peak was detected in the sample versus everything else. Okay. So you can do with an XRD, you can do compositional analysis of your sample and say, okay, I've got 30% calcite in there, 20% quartz, and I don't know, 50% plagioclase in my sample. So, but the highest peaks here are called primary peaks. These other ones here are called secondary. So what you want to look for, and there's databases that are dedicated to this. Like you go on mindat.org, they have pretty much for all the really well-known minerals, they have the D spacing or the XRD pattern for those minerals. So if you want to compare your scans to basically what the standard is for that mineral, you can. So for calcite has a peak that's usually about 29 degrees. Quartz usually has one that's about 26. All right, primary peak. So when you run a sample, this is what it looks like. It gives you a readout that's in raw data. So unless you have a program, usually the program that I've used the most is Jade. Okay. And that's actually the program that most everyone uses. There's not a really good shareware version, so you have to sort of shell out for the license for it. But what we can see here are the X-ray pattern for a sample that's been scanned. And we can see that the scan ran from about 17 degrees to 35.5 degrees, and we can see that it has that the database picked up that there's quartz, fluorite, epidote, hornblende, albite, augite, and anorthite present there. And this particular sample was of greenstone, so it's not surprising that we see those minerals in there in those abundances. So, here we have another X-ray antigerite, which is a variation of serpentine. Okay. And lizardite, another example of serpentine. All right. So, that's basically XRD. Okay. And it's mostly just sitting down at a computer once you have all your data and looking at it and running through and looking at the different XRD patterns and trying to figure out, okay, because the program will automatically identify the majority of your peaks, but there's some that you have to go through and you have to click on them and then figure out, okay, what peak does this belong to, and basically through trial and error figure out what the peak is associated with, what mineral it is. And you can run through and try different elements, and you can have it scanned through the database again and keep running it through to eliminate your choices. So, yeah.